Yeah, welcome to today's lesson. Today's lesson will be treating gas laws, and specifically we'll be treating the ideal gas equation. So in our previous lesson, we talked about gas laws, but we were talking about Boyle's and Charles' law. So and at some point we talked about how these two laws combination can lead to the formation of the new equation that's called the ideal gas law. So we'll be treating this ideal gas law in this lesson and seeing how the combination of the Boyle's law and the Charles law led to the formation of the ideal gas laws. So ideal gas law, also known as, or popularly known as the ideal gas equation, is a fundamental relationship in chemistry that describes the behavior of gases under varying conditions of pressure, volume, and temperature. It provides a comprehensive expression of the earlier individual gases or gas laws, and critically, it tries to predict gas behavior in chemical reactions and laboratory experiments. So this ideal gas law is, as much as it's called the ideal gas law, and I said at some point in our previous lesson, I said ideal gas laws are perfect and they are said to be perfect and they don't really exist per se. However, in real sense, these real gases that we know, they behave very much like ideal gases in most cases. So that's why this ideal gas law is actually very useful in several locations. So we'll be seeing how this would apply and seeing what it looks like even in this lesson. So let's see what the ideal gas law or the ideal gas equation looks like. So I'll be interchangeably using the word ideal gas law for ideal gas equation. So the ideal gas equation states that it's just mathematical expression that shows that the product of pressure and volume is equal to the product of the number of moles and temperature with a gas constant known as R. So this is the formula. The formula is equal to PV. The formula is PV equals to nRT, where P stands for pressure, V volume, N number of moles, R the gas constant or universal gas constant, and T representing the temperature in Kelvin. So specifically in Kelvin. So this equation combines Boyle's law and Charles' law. So if you look at this equation, it has P, V, and T, and it looks so much like the Boyle's law. If you remember when we were throwing the Boyle's law formula, I said we were putting PV equals to K. And at some other point, we said V over T is equal to K. So it's similar to this law. So, but this law is not just a combination of just the Boyle's law and Charles' law, but a combination of both the Boyle's law, Charles' law, and also the Avogadro's law. In one expression that it's a combination that in one expression it tries to describe how gases respond to change in physical conditions. So let's see these laws and see what they state. So the Boyle's law, even from our former lesson, we know that the Boyle's law states that the volume of a gas is inversely proportional to its pressure at constant temperature. And we also learned that the Charles law states that the volume of a gas is directly proportional to its absolute temperature when pressure is constant. So I told from the previous class, I said the both laws, Boyle's and Charles law, are talking about volume. But now seeing how they vary at different conditions like changing pressure and also changing temperature. So these two laws were combined with another law known as the Avogadro's law. And the Avogadro's law states that equal volume of gases contain equal number of molecules at the same temperature and pressure. So this Avogadro's law, due to the relationship with pressure and temperature, which Boyle's and Charles' law were also involved with, it also introduced an extra component known as the number of moles. So the number of moles, according to Avogadro's law, it says that the number of moles is the same at all temperature, at the same temperature and pressure. So that's the simple definition, or I'll call the simple statement for the Avogadro's law. It states that equal volume of gases contain equal number of moles at the same temperature and pressure. So let's see what the universal constants in our general ideal gas law formula. These are ideal gas law. We said that it is PV equals to nRT. So we said P is volume, P is pressure, V is volume, T is temperature, N is number of moles, and R, we said it is the gas constant or universal gas constant. So let's see what this universal gas constant looks like. So this universal gas constant is actually a constant that has a specific value, and this value has two parameters or two units. So the universal gas constant could be given to you in terms of atmosphere in terms of atmosphere and number of moles. It could be given to you in that form, and it could also be given to you in terms of joules per mole per Kelvin or joule per mole Kelvin. So let's see how this universal gas constant can be used. So it has two values. The first value is 0.0821 liter atmosphere per mole per Kelvin. That's how it's being called. So while the second value is given as 8.314 joule per mole per Kelvin. So when pressure is measured at atmospheric pressure, at atmosphere and volume, we use this value, this 0.0821 value. But when it is not measured in that condition, when they did not tell you that, they did not mention atmosphere for pressure, when they did not mention atmosphere for pressure and liter for volume, you would have to use the 8.314 formula. So those are the times you will use these two formula. So when they don't give you temperature, when they don't give you pressure in atmosphere or volume in liter, you would use this 8.314. But when they give you volume in liter and atmosphere in temperature, you use this 0.0821 formula. So the choice of units for R must be consistent with the units used for other variables in the equations. That's what I'm trying to say, that when they give you liter, you know that you should use the value of R that has liter, and you need to change every other pressure to atmosphere. You get? So once you are given liter or you are given atmosphere, if you'll be using the 0.0821, all the parameters, both pressure and volume, should be according to the units. If you are using the 8.314, all the parameters should be in SI units, because 8.314 is SI units representation for the universal gas constant. So any mismatch can result in an error in your calculation. So the ideal gas equation is widely used to calculate unknown properties of gases, such as determining the number of moles in a container or estimating the pressure a gas will exert under certain conditions. It assumes that gas particles do not attract or repel. So remember, from the kinetic molecular theory, we said that the kinetic molecular theory stated that ideal gases or gases, they don't have any form of attraction or repulsion. So that law was actually part of what was used in this ideal gas equation. The assumption from that kinetic molecular theory was what was used in the generation of the ideal gas law. And this ideal gas law is assuming also that, according to the kinetic molecular theory, that gases, they don't have any form of attractive force or repulsive force with themselves, and also their volume is insignificant. As I said, it assumes that gas particles do not attract or repel each other and occupy no volume themselves. They assume that the volume of gases are insignificant. So although this equation is termed the ideal gas law or the ideal gas equation, most real gases, as I said in the beginning, real gases approximate behavior under many conditions is the behavior of ideal gas. So real gas approximate this behavior under many conditions, particularly at high temperature and low pressure. So at high temperature and low pressure, real gases behave very much like ideal gases. So when temperature is increasing, real gases will behave like ideal gases. And when pressure is also reducing, real gases will also behave like ideal gases, but they will begin to deviate when we start seeing high pressures or low temperature, or high pressures and low temperature. So where the interaction between gases and gas particles can no longer be ignored. So now, in conclusion, these ideal gas equation can be used to predict and analyze gas behaviors in a wide range of scientific contexts. It unifies multiple gas laws into a single formula and is useful for theoretical and practical applications. So this ideal gas equation is very useful in chemistry, and as I said, most gases to a large extent behave like ideal gases, and as a result of that, the ideal gas equation is very valuable in the field of chemistry. So with that being said, that will be the end of this lesson. With all this being said, this will be the end of the lesson. Bye.